All right, this is video 2 of chapter 11-13. We're going to take a look at some free response questions. Let's begin with number 24. We have two types of intermolecular forces present in liquid H2S, which are London dispersion forces and dipole-dipole forces. So they're going to ask us to do some explanations about these forces. Compare the strength of the London dispersion forces in liquid H2S to the strength of them in liquid water. Now we're only looking at dispersion forces. Later we're going to compare the dipole-dipole forces. So dispersion forces are going to be stronger in which one? Now, if you take a look, both of them look very similar, H2S versus H2O. But because sulfur itself is actually bigger, if you take a look at the periodic table, sulfur actually sits right below oxygen in group 16. And so sulfur being bigger is a bigger atom which will have bigger dispersion forces. So H2S will be the answer. You always want to give the answer they're asking and then an explanation. You want to say because, and actually for the AP exam, why don't we, you don't even have to write because. The rationale is sulfur is a bigger atom containing more electrons. Making the molecule more polarizable. That's a good word. Making the molecule more polarizable. Polarizable. These are actually good terms to use. Polarizable, just like effective nuclear charge was a good term to use in the periodic table chapter. And notice the connection. The word polarizable is good to use when describing dispersion forces. Now, B says compare the strength of the dipole-dipole forces in H2S and water. Now, dipole-dipole forces, both of these are actually polar. And the reason both are polar, we know famously water is bent, but H2S will actually have the same shape because it's in the same group, so it reacts just the same. So H2S is also bent. It has the same number of valence electrons. So both of them are bent. Because they're both bent, they're both polar because they're asymmetrical. Now, the dipole-dipole forces are actually stronger in water. This is because oxygen is more electronegative. The more electronegative you are, the more you would pull the electron density toward yourself, creating a more negative and leaving with a more positive on the other side. So now water also has hydrogen bonding, and we talked about this. You may know that this is also hydrogen bonding. They're not asking us about hydrogen bonding. They're asking us for dipole-dipole. Now, I have said that hydrogen bonding is like an extreme version of the dipole-dipole force, but the dipole-dipole force is a separate force usually considered. So I would actually talk about the fact that H2O, and so H2O would be the answer now, and then you want to say oxygen is more electronegative. Resulting in a more drastic charge distribution, you can say if you want to be fancy, or you can say pulling electrons more toward the oxygen, creating a bigger difference. You can say in electrode density, you can say a bigger difference in the pole, bigger difference in the polarity. How about that? That's good. If you describe this a different way, as long as you've identified who it is and talked about oxygen being more electronegative, that should be sufficient. Take a look, very similar question. I want to take a look at number 26. Actually, number 26 is a bit different. Right. So here we're asked about two compounds, SO2 and SiO2. Now, if you take a look, SiO2 is silicon, is a semi-metal, whereas sulfur is definitely a non-metal. Non-metal. They're actually going to be, so semi-metals are kind of approaching metals. Remember, if you would have something like magnesium oxide, then you got yourself an ionic compound. Ionic. Which means SiO2 is kind of approaching halfway there. Now we know, notice that the boiling points, 1800 versus 201. SO2 is actually a gas. This is below the freezing point of water, 273, which means it's a gas at room temperature. This guy right here has a drastically higher, so it can't be due to intermolecular forces. You can't say that the intermolecular forces of SiO2 are stronger. You will not get a number this high for this being a molecule. This is actually not a molecule. It's actually a network covalent solid. We talked about these briefly in Chapter 9, network covalent solid. So take a look at Chapter 9 and the notes. So essentially what you have is you have silicon dioxide, this is glass, by the way. Silicon dioxide, you may recognize it as glass, actually forms huge covalent bonds, essentially, and then you got oxygen, oxygen. So you have silicon and oxygen in covalent bonds all throughout the molecule. So you have, essentially, you have a humongous macromolecule with very strong covalent bonds, and that's what you're breaking, and that's why the temperature is so high. This temperature is comparable to the melting points of ionic compounds. Ionic compounds all have very strong lattice energies, positive, negatives, requiring a lot of energy to break. So actually, what you want to say is that SiO2 has network covalent bonds. You can say that. I would say, yeah, it has, how would we say, network covalent bonds. If you happen to remember this example, they'll oftentimes try to test if you know what an so this is not a molecule, so you can't really say that SiO2, because remember, to get a molecule you have to be able to have a separate unit that exists on its own. So this separate unit does not exist, so it's not a molecule. So if it's not a molecule, you can't describe intermolecular forces. So you do not want to talk about intermolecular forces, no intermolecular forces here. Same thing if you had to account for ionic solids melting point, you would not talk about intermolecular forces. You actually talk about charges, and you would talk about the size of those ions. That's the idea. Not bad? Let's take a look at the question, a question on the back, the very last one on here. Last page. Right. So we have ourselves two processes given to us on the right. And bromine, the standard state of bromine is a liquid, whereas the standard state of iodine is a solid. We know that from the periodic table. Enthalpy change for the formation of Br2 and I2 from these elements are shown on the right. Now this shows us just the becoming a gas in both cases. Notice we begin with liquid to a gas, solid to a gas. This is the enthalpy change, which is the energy change to become a gas, which is a measure of how strong the intermolecular forces are. This is intermolecular forces strength. So melting point is strength, is a measure of intermolecular force strength. So they want us to explain why delta H for the formation of iodine is larger than for the formation of bromine. And then we want to talk about the interparticle attractions, the same thing as intermolecular forces. That's another word for interparticle attractions. Trying to maybe throw you off a little bit. Now you'll notice because iodine's melting point is higher, it has stronger IMF. So you it tells us that. And so what we want to do is rationalize why. Now iodine, if you take a look, iodine is actually lower on the periodic table than it's right below bromine. So you go bromine, iodine, and iodine is bigger. Iodine is a bigger atom. So we want to definitely mention iodine being bigger. I'll kind of talk through this, and then you can maybe put down the answer. And so another reason why, so iodine is bigger. So we'll say this. Let's actually put it down. So we have London dispersion forces. Go and write this out. London dispersion forces are stronger in I2 because iodine is a bigger atom. Iodine has, how about a larger radius? How about that? Larger radius than does bromine. Not bad? So along those same lines, by the way, you can also say this, well, you can also recognize that because iodine is going from a solid to a gas, we're actually completely breaking the forces here. Whereas we're not completely, we're going from a solid to a gas, so more forces have to be broken. Think of it that way. So you can actually also add, and that won't hurt, we're going from a solid to a gas in iodine versus liquid to a gas in bromine. That will also make this a higher number, because they're asking for why I2 is a higher number than Br2. All right, C says I2 and Br2 then can react to form IBr. Predict which would have the greater molar enthalpy of vaporization. Molar enthalpy of vaporization, same idea. Which one will it be higher, harder to vaporize, more energy? So because IBr is polar, and because iodine is bigger than bromine, this one actually wins on two counts. Wins in the dipole-dipole forces. It also wins in the London dispersion forces. So this one will definitely win. So you could say IBr, so identify the correct answer. You don't have to circle it, IBr. And then we want to say polar. Polar, because we'll say IBr, polar. IBr is polar. I'm having a little trouble with is polar. Also, iodine is bigger than bromine. Those would be the two answers. If it's a 2-point question, they'll give you both points. If it's a 1 point, they may just accept either one as an explanation. Right, so let me just mention, okay, let's do the last one here, which is part D. And this gets into solubility. We'll do this one quickly. So we have a student is performed, experiment is performed, student is not performed, comparing the solubilities of I2 in hexane, water and hexane. So we have H2O and hexane. A student adds 2 mils of water and 2 mils of hexane to a test tube. So we have a test tube. Now, water is almost always more dense. So water will be down here. Hexane C6H14 is up here. Remember how we talked about, think of this as a long nonpolar molecule with 6 carbon atoms. Long nonpolar molecule. So it's nonpolar. The student then drops a small crystal of iodine into the test tube, then corks it, inverts it several times. The hexane layer becomes light purple. This is because iodine, which was thrown in here, went to the bottom, and then iodine dissolved in the hexane. Now, the reason why iodine dissolved in the hexane is because hexane is nonpolar. It did not dissolve in the water because the water is polar. So that's what you want to say. So hexane is nonpolar, which mixed with, or which matches, you could say, matches the intermolecular forces, the London dispersion, well, not London dispersion, because water also has London dispersion. The intermolecular forces of I2. You can also say that, I would also say that water is very polar and exhibits hydrogen bonding. Exhibiting hydrogen bonding. So, bonding. You were able to, usually whenever they ask a question about 2 different compounds, I would explain or mention both of them. So hexane and water. So this is the idea that like dissolves like. All right? Do the rest of the questions and make sure you can explain intermolecular forces. We'll see you in class.